So let's go over our param block. As I said in the last video, our param block is where we define any parameters of the model. This is analogous to both $theta, $omega, and $sigma in Omen. Here specify all of the parameters that we want our model to infer, to estimate. And we specify them in a begin and end block. And we can pretty much say the name of the parameter and to specify what type of parameter we are going to use Puma's domains. We say that this parameter leaps, it's in with the \in and LaTeX command. We say that it is a domain. So for example, an alpha would be in a real domain. That's a real number line, so it's a scalar. And as you can see, it has no positional arguments and a lower upper keyword arguments with default values as -infinity and +infinity and initial values of 0. So by default, it's an unconstrained parameter. So it can take any values in the whole real number line. So that's okay for an alpha, for example. For a typical occurrence, we'd probably want something that is constrained to the positive values, so something like lower equals 0, 0, 1. And we can also do the same thing for our sigmas. Now, suppose you have a theta, vector of parameters. To specify vector of parameters, you take something in. Instead of real domain, now you say vector domain. So this tells that our parameter is a vector with all of the elements being by default unconstrained in the number line. So they are real scalars inside every element of our vector domain is a real scalar and the initial values are 0. And there is one required positional argument, which is the length of our vector. So if we say that our vector is length 3, we can use that in our pre-computations block. So θ1, θ2, we can index, we can slice those. So it's pretty much a vector. Now for matrices, we have two domains. We have first the diagonal, the positive diagonal domain, that's E-diagonal domain. And this is a diagonal matrix constrained to the positive domain. So this is a good matrix for diagonal. For various matrix where we are not implying that there is a covariance between the elements, just variance because it's diagonal matrix, and there is one required keyword positional argument, which is the dimension of our square matrix, diagonal square matrix. So if we say that is a p-diagonal domain 2, that specifies that our omegas is a 2x2 diagonal matrix. We can also specify full matrices with the PSD domain, and this will give us a full positive semi-definite matrix, which is pretty much the constraints that we need for a covariance matrix. And then as in the diagonal domain, we specify the dimension. So if we say 3 is the 3x3 matrix. And we also have off-diagonal elements here because it's a full positive semi-definite matrix. Now, these are the 4 domains that we have available in Pumas. They're real domains for scalars, vector domains for vectors. We can specify matrices with either diagonal, positive diagonal domain, or full matrices with the positive semi-definite domain.